Hi everyone. Today let's talk about how to use the normal distribution to approximate the binomial distribution. So do you remember in last chapter, when we talk about the Poisson distribution, we can use the Poisson distribution to approximate the binomial distribution when n is large and p is small. Okay, so today, how about when p is not small? Well, if n is large and p is not small, then not small, I mean which is close to 0.5, then we can use the normal approximation. Okay, so let me put it here. Okay, so we know that for the binomial distribution, we can use PMF to calculate, or we can use CDF to calculate. However, if we use our table 1, our n only get up to 20. Okay, so that's why if with a large n, we're gonna use other distribution to approximate it. Okay, so when n is large, p is small. How small? It's like 0.1 or 0.2. Okay, those are small. Then we use Poisson distribution to approximate it, with the lambda is n times p. Okay, and we use the CDF values in table 2 to calculate the Poisson distribution. When n is large and p is not small, I mean close to 0.5, then we're gonna use the normal distribution to approximate it. And because the normal distribution is a continuous distribution, right? When we use continuous random variable to approximate discrete random variable, what do we need? We need to use continuity correction. Okay, how about when n is large and when p is also large? So when p is large, I would say large is like 0.8, 0.9. So those are large. So in this case, you can actually flip it. You define your success to be the failure. Okay, so we define your success to be the failure. Now your p is 1 minus the old p. So then, because your old p is large, so your new p is small. Then you can use Poisson distribution to approximate it, right? Because binomial distribution, let's say we have we flip the coin 10 times and we count the number of heads. Well, if p is large, well, you can think about, okay, if the probability of getting a head is large, well, we can let our success to be getting the tail. Then probability of getting the tail is small, right? And then the number of, let's say if you want to find the probability that you get 3 head out of 10 flips, then now you're looking for, we're gonna find the probability of 7 tail out of 10 flips. So you actually just like redefine the success to be failure in this case. So that's why when p is close to 0.5, we use the normal distribution. When p is not close to 0.5, is either very small or very large, then we use the Poisson distribution to approximate it. Okay? Alright, so let's come back to our theorem. So the theorem, normal approximation to the binomial distribution. This theorem is also called the central limit theorem for the binomial random variable. So let Sn be the binomial distribution with the parameter n and p. And suppose a less than b, then the probability, the limit of the probability of our binomial distribution lies in the range of A and B. That will be when n goes to infinity. That is the CDF values of the standard normal distribution when you use the phi of B minus phi of A. Okay, and this is a picture of it. So we have A and B. You can compute the area between A and B. That is the probability of the normal distribution. Okay, so by the way, we know Sn is the binomial distribution. We can approximate it by the normal distribution. And this guy, you see, E subtract, this is the mean of the binomial distribution, and this is the variance of it. So you're standardized the binomial distribution. So this standardized binomial distribution is well approximated by the standard normal distribution when n is large and the p is close to 0.5. Okay, so rule of thumb, if your variance is greater than 10, then the approximation is good enough. Okay, so that's the rule of thumb. So let's look at example 1. 20% of the memory chips are defective. Choose 100 randomly in a lot. Find part A. The probability of at most 15 will be defective. Part B. Exactly 15 will be defective. Okay? Yeah, and remember that the table 2, okay, the CDF for the binomial distribution is only the n is only at most 20, but here we have 100, so that is large. So we have to use either Poisson distribution or the binomial distribution to approximate it. But here, our P is 0.2. You might say, 0.2 is like small, isn't it? Okay, then remember our rule of thumb. Okay, when the variance is greater than 10, then the approximation is good enough. So let's see. So our mu is n times p, which is 100 times 0.2. So 100 times 0.2 is 20, right? And the variance is n times p times 1 minus p. So those are the mean and variance formula for the binomial distribution. So 100 times 0.2, 1 minus 0.2 is 0.8. So the answer is 16. You see, 16 is greater than 10. So that's why by the rule of thumb, we can use the normal distribution. Okay? So we remember that the CDF for binomial distribution is the n is only at most 20. Do you remember the Poisson distribution? So if we come back to our table, so if we go to the Poisson distribution, well, your lambda is 15. Okay, your lambda is 15. So you see in this problem, if we want to use the Poisson distribution to calculate, the lambda is NP, and here is 20. But in our table, let me put a different color here to emphasize. Okay, in the Poisson table, the lambda is at most 16. Let me make sure. 15 is at most 15. So that's why when your lambda is greater than 15, you either use some online as the calculator, or you should use another distribution. Okay. Next. So we're gonna use the normal distribution to approximate it. So part A. Probability at most 15 will be defective. At most. What does that mean? At most. less than equal to 15, right? And we know that x has the binomial distribution, so this is a discrete random variable. Okay, and then we want to use a normal distribution to approximate it. Well, less than 15, less than equal 15, that includes 15, right? When you want to use a normal random variable to approximate it, let's say that is y. Y is the normal random variable, which is continuous. So you want to have less than equal to 15. So you want to include 15. So this is 15.5. Okay, and you want to count all of those. So y is less than equal to 15.5. Okay, so this is a continuity correction. Alright, so after we get the normal distribution, we want to change it to the standard normal distribution. So in this case, we have y minus mu over sigma. So if you do this operation to the y, you also do the same operation to the 15.5. Okay, mu, do we know mu? Yes, that's 20. Do we know sigma? Well, sigma squared is 16, then sigma is 4. So this guy is z, so we have z less than equal to 15.5 minus mu. Mu is 20 over 4. So plug this in our calculator. What do we get? So 15.5 minus 20 over 4. So the answer is minus 1.13. So for these values, it's only to keep 2 decimal places. Because if you can remember our CDF values for the normal distribution, the z values are only like 2 decimal places. So what we're looking for, negative 1.13. So negative 1.13. Where's 3? Here. So negative 1.13 is 0.1292. Okay, so that's v of minus 1.13. That is 0.1292. So this is from table 3. The CDF values for the normal distribution, standard normal distribution. Alright, so this is part A. Okay, can you pause here and try to work on part B before we continue? Are you done? So here we have exactly 15. What's exactly 15 means? Well, exactly 15 is what? So 14.5 to 15.5. So we have 14.5 less than equal to y less than equal to 15.5. Okay, so y is the normal random variable, is continuous. In order to calculate it, we're gonna change it to the standard normal distribution. So we subtract mu over the standard deviation, which is 4, less than equal to z. So that's z, right? After you subtract mu and over sigma. And then this guy is 15.5 minus 20 over 4. Okay, this number we already know. This is like we already calculated in part A. Okay, so we have z less than equal to negative 1.13. Well, good. This number, let's plug this in our calculator. So 14.5 minus 20 over 4. The answer is negative 1.38. So here many students make some mistake when they round the numbers. So when you round the numbers, okay, so if you have 4, then you just erase it and get 1.38. But if you have like 5 or 6 or 7, you round up, it becomes 1.39, for example. Okay, so I realized many students had a round up error. Okay, so that is the CDF of the bound, okay, and minus the CDF of the initial value. So final value minus initial value. So we plug in phi of negative 1.13. We already know from part A. That's 0.1292. How about next one? Well, let's go back to our table. Negative 1.38. Where's 8? Oh, this guy, right? So it's 0.0838. So 0.0838. So plot this in your calculator. What do you get? So I get 0.0454. Do you have the same answer? Yay! Let's continue. Okay, example 2. Roll a fair die 120 times and advance 2 or 3 steps if the result. So advance 2 steps if the result is 1 or 2, and advance 3 steps if the result is 3, 4, 5, 6. Okay, and then approximate the probability of we move more than 315 steps. Okay, so let's see. Let X be, let me change back our color. Okay, so let X be the number of steps we move. So far, so good. So let B be the number of row 1 or 2. So that's like the success, okay? If we roll 1 or 2, we advance 2 steps. If we rolled 3, 4, 5, 6, we advance 3 steps. Okay, so this is like a binomial distribution with the number of trials is because we're rolling a die 120 times. So we have 120 trials. And what's the probability? What is the probability you get either roll 1 or 2? Well, how many? So this is a fair die. There are 6 outcomes. And here 1 and 2 is like 2 outcomes out of 6 outcomes. So the probability is 1/3. So far, so good, everybody? So it's a binomial distribution with the n is 120 and the success probability is 1/3. Okay, let's figure out the mean and the variance. The mean is n times p. So I hope you all can remember the a mean and variance formula for the binomial distribution. Okay, if you don't remember, it's okay. You can always look it up from the formula sheet. Okay, so 120 times 1/3 is 40. And the variance NP 1 minus P, so it's like 40 times 1 minus 1/3 is 2/3. So like 80 over 3. Well, of course, this guy is greater than 10, right? Remember our rule of thumb. Okay, if the variance is greater than 10, then the normal approximation. So normal approximation is good enough. Okay, sorry, I mean greater than 10. Okay, next let's start. So probability of X greater than 315. What is the relationship between x and b? Okay, let's figure out what's the relationship between them. So, x is the number of steps. Okay, b is the number of rows, 1 or 2. Okay, so if you get row 1 or 2, you advanced 2 steps. So it's like 2 times b, right? And you advance 3 steps when you get the row 3, 4, 5, 6. How many rows? Well, think about it. We have 120 trials. Like B is like the success, you get row 1 or 2. So if you have B success, how many failures? Well, that is 120 minus B, isn't it? If you have B failures, the total is 120. And the number of, if you have B success and the total is 120, then the number of failures is 120 minus B. Okay, so let's distribute it. We get 2B plus 360 minus 3B. So that is 360 minus B. So far, so good, everybody. So that is my x. So let's plug it in. X is 360 minus B. And we wanted it to be greater than 315. Okay, what does that mean? So that means we can move the B on the other side. 360 minus 315. So B is less than 45. So this is the same as saying B less than 45. Okay? Alright, let's see. So B is a discrete random variable. Okay? 45 is here, less than that. Then, which means when you want to use a normal random variable to approximate it, you don't want to count the 45, so you want to count the 44.5. Okay, and this. So this is probability of y less than or equal to 44.5. So here y is the normal random variable. It's a continuous random variable. Okay? So after we get a normal random variable, that's not enough. We need to change it to the standard one. So the standard one is you subtract the mean, which is 40, divided by the variance. Divided by the standard deviation, which is the square root of the variance. And we do the same thing to the 44.5. Okay, so what is that? That is z less than or equal to, so plug in your calculator. We have 44.5 minus 40 divided by square root of 80 over 3. Yeah, so make sure your parentheses, when you plug in your calculator, your parentheses location is correct. Okay, so what I get 0.87. Okay, so that is less than or equal, great, that's exactly the CDF. If we don't get like less than or equal, maybe we need to like change. Alright, so let's come back to our table. The z value is 0.87. What's the probability? 0.87. Next page. So 0.87 here. So it's 0.8078. So that is 0.8078. So this is from table 3. Okay, so this is our answer for example 2. This example is quite interesting because first we defined our x. X is the number of steps. And you realize x is not a binomial distribution, but it's kind of related to a binomial distribution. So the b is the number of row 1 or 2, okay? So getting row 1 or 2 is considered as success. So B is the number of success in 120 trials. So that is the binomial distribution. So you're going to relate X to the B, and then you use the continuity correction, use the normal random variable to approximate it. So that's why we get the Y. And after you get the Y, you have to change it to the standard normal distribution, because we only have the table for the standard normal. We don't have the table for normal. So change to standard normal distribution, and then use the CDF value to calculate. All right. So that is 5.3. Let's continue to look at section 5.5, the uniform distribution. So uniform distribution, what does that mean? It means over that region, let's say A and B, we have the same probability. So the probability are the same. Okay, and it's 0 otherwise. Okay. But we know the total probability is 1. So the area is 1. Well, then what is the height? You know, this guy is B minus A. Then what is the height? You want to make the areas 1? Well, then the height must be 1 over B minus A. Right? So that is why we have this PDF. Okay, when x is between a and b, f of x equals to 1 over b minus a, and the function is 0 otherwise. Any random variable whose PDF is f has the uniform distribution on AB. We denote x has the uniform distribution from AB. Some of you might ask, okay, what happens if we put like this point there? Well, it's okay. Remember for the continuous random variable, the endpoint doesn't matter. So if you put equal here, it will be the same, still uniform distribution. Okay, that's why sometimes some textbooks use the definition. We have less than equal and less than equal here. Okay. All right. So fact, if x has the uniform distribution, then the mean equals to a plus b over 2. And the variance equals to b minus a squared over 12. Okay, so here I actually want to prove this with you. So in the exams, you will have like problems to ask you to find, giving you a function PDF, and then you want to figure out the mean and variance. So this is a good exercise, okay, where we're given the PDF. Okay, how do we find the mean and variance? Okay, let me see. What color do you like? Do you like green? Okay. So what is mean? Mean is integral x times f of x dx. So that is the definition. But in our example, it is 0 outside of the interval from a to b. So that's why here we plug in integral from a to b x times 1 over b minus a dx. 1 over b minus a is a constant, so we can move it outside, right? And integral of x is x squared over 2. We evaluate from a to b. So that will give us, so we plug in b first. Okay, so we have b squared over 2 minus, we plug in a, so a squared over 2. Okay, what is that? Well, you can see we can figure out the 1/2, and then the top we have b squared minus a squared. If you can remember, That is b plus a, b minus a. Wow, they cancel, so we get a plus b over 2. So that is exactly what we want to show. Alright, so that is the mean. How about the variance? Do you remember that for variance, we use the second moment minus the mean square to calculate. So let's calculate the second moment. Okay, let's make it more colorful. So second moment is replace x by x squared. So we have x squared and the rest the same. We can still pull it out. What is the integral of x squared? Well, x cubed over 3, right? Over a, evaluate from a to b. And then we have 3 times b minus a. And then at the top we have b cubed minus a cubed. Do you know how to factor it? So b cubed minus a cubed is actually b minus a. And then b squared plus ab plus a squared. So this is how we factor it. You can see b minus a cancel, so we have a squared plus ab plus b squared. So I like to reorder because usually we put the a first and then the b. Alright, so that is the second moment. Now is the time to figure out the variance. So variance equals to the second moment minus the mean squared. So second moment minus the mean. What is the mean? This guy. So this guy squared. Wow, 2 squared is 4, but then the top we have we have a plus b squared. Alright, let's see. A squared plus ab plus b squared, and that's over 3 minus 4 of square, so multiply out a squared plus 2ab plus b squared. We take the common denominator, that's 12, and then this guy we multiply by 4, so 4a squared plus 4ab plus 4b squared. Subtract that guy multiplied by 3, but because of subtract, we also distribute the negative. So minus 3 times 2, 6ab minus 3 times b squared. Okay, so we play with the algebra. Alright, let's combine them. The like terms, 4a squared minus 3a squared is a squared. 4ab minus 6ab, so minus 2ab. 4b squared minus 3b squared is b squared. Well, if you can notice that the numerator is exactly the complete square of a minus b, right? Okay, so we get this is our answer. Oh, are they the same? Yes, they are the same because square always positive, so b minus a squared is the same as a minus b squared. So we actually get the same result. Yay! Okay, let's look at example 1. Alright, the random variable x is uniformly distributed on the interval from 2 to 5. Find the following. Okay, so uniform distribute on the interval 2 to 5. Let me draw the picture. So 2 to 5 right here. So it's uniformly distributed on 2 to 5. Okay, part A. Px less than 3. Okay, less than 3. Where is 3? So 3 is right here. So less than 3 is this guy. Okay, so how do we calculate the probability? Well, you use you use the ratio, right? You use 3 minus 2. Okay, this is what we want. Over the total. What's the total? 5 minus 2. Well, 3 minus 2 is 1. 5 minus 2 is 3. So this is the probability of x less than 3. So far, so good, everybody? Okay, B. How about the probability of 3.5 less than or equal to x less than or equal to 7? So we draw the picture again. 2, 5. Where's 3.5? Somewhere here. Where's 7? Here. So we want to look at this. But the problem is 0. The f is 0 outside of 2 and 5. So we only get this piece. So we have this piece on the numerator. Over the total, what's the total? 5 minus 2. And what do we get? So 5 minus 3.5 is 1.5. Over 3 is 1/2. So that is our answer. So here you gotta be careful. So here, those guys are zeros. Okay, when it's outside of 5, is 0. So this guy is 5. This guy is not 7. So we have to be careful. Okay, so this guy is not 7. Be careful with that. Okay, so part C. So part A and part B, we were given the x values. We want to find the probability. And part C, we're actually getting the probability, and we want to find the x values. Okay, so let's do that. Oops. Let me use blue. Okay, so C, same thing. We have 2 to 5. That's our interval. We want to find the x values such that the probability of x greater equal to x, this proportion is 0.7. So 0.7 is p of x greater equal to small x. But that is the numerator 5 minus x over the denominator 5 minus 2. So this is 5 minus x over 3. Well, that is 0.7. So let's solve for x. We multiply by 3 on both sides. We get 2.1 is 5 minus x. Both sides add x and subtract 2.1. We get 2.9. So our x values is 2.9. So far, so good, everybody? Okay, and then find the mean and variance. Find the mean and variance. So in this case, our uniform distribution is on the interval 2 and 5. So 2 is like our A. 5 is like our B. Then we can use our formula. Mean is A plus B over 2. Variance is B minus A squared over 12. Okay, so mean is A plus B over 2. So that's 2 plus 5 over 2. 2 plus 5 is 7. 7 over 2, 3.5. And the variance is B minus A squared over 12. B 5, A 2 squared over 12. That is 3 squared over 12. Well, you can cancel the 3. We get 3 left and 4 here. So that is the variance. But we are looking for standard deviation. Standard deviation is the square root of the variance. Well, square root of 3, square root of 4 is 2. So we can leave our answer like that. Alright, so that is the uniform distribution. Alright, bye.